Hello and welcome to this printed solid-state lithium-ion batteries for the future webinar. My name is Tero Leppänen from the University of Oulu, and I'm the project manager of printed applications in solid-state batteries project. First, I'm going to briefly introduce what this project is all about, and then we are going to head into the main topics for today. If you have any questions at any point during our presentations, there is a link down in the description box below where you can leave them, and we'll be answering them to the best of our abilities. So, printed applications in solid-state batteries or PAS project is a research, development and promotion project funded by the European Regional Development Fund, Council of Oulu Region, City of Oulu and Printocent. Project duration is 2 years and budget a bit over 800,000. The main objective of this project is the production of a battery cell prototype with a solid electrolyte and the manufacturing of cell with printing technology. In addition, we are also supporting business development in the area by looking at what is needed to start manufacturing these batteries of the future here in Oulu. And we are doing some value chain and business ecosystem modeling and development related to that. The project is coordinated by the University of Oulu and partnered by VTT Research Center and Oulu University of Applied Sciences. So basically in this project we are developing these new battery and printing technologies of which Ulla and Riikka will shortly tell you more about. And then we are also testing these new solutions and considering the applications and end users as well. And without further ado, I'm handing the stage over to Ulla, who's going to tell you more about solid-state battery technology development. Ulla.
Good morning, everyone, and welcome to this seminar also on my behalf. As a principal investigator of this project, I will shortly explain you on a general level what are the aims of the project and what is the final aim after the ending of the project. So that is the first seminar we will organize, and of course we will organize 1-2 more seminars during the project. So you are also welcome to all of those. So my background is very strongly in lithium-ion batteries. I have worked with that topic 15 years, and of course, as you know, that is now a very hot topic also for Europe and especially also now for Finland, and very important topic as well. You might ask us that why we are working with the lithium-ion batteries. Why this technology? Because there are of course a lot of other potential technologies for energy storage. Our aim in PAS project is to work in very close collaboration with the companies and to be very close to the real application for our industry and business. And that was the reason why we selected lithium-ion battery technology to develop a new battery preparation method technology, screen printing, which we will today also look at a little bit more detailed. Lithium-ion batteries have a long history, around 30 years. But based on my very famous European colleagues, they estimate that lithium-ion batteries will also have a future of 30 years. So it is not an old-fashioned technology, as you might somehow know and hear from the public discussion. What we are aiming here in our project is to make also not only a new technology for making battery cells, but also at the secondary aim to develop the existing lithium-ion battery technology to be more sustainable. What are actually the needs to improve the sustainability of the existing lithium-ion batteries? From the early beginning, there was some challenges with the battery safety. Now we have improved a lot already for nowadays, the battery safety, but there are still a lot of work we can do and make batteries also better from that viewpoint. When we are assembling battery cells, there are a lot of issues we can still develop it. We can use a greener solvents. We can replace, for example, some toxic solvents we use in batteries, and we can replace some binders and even electrolyte salts to be materials, for example, containing no fluorine compounds. And of course, we can always make an attention to improve the energy density of lithium-ion battery cells. Not only the gravimetric energy density, but we can also improve the volumetric energy density. We know how to make battery cells. We know how to make cells with the traditional technologies. And I'm sure that if we know how to make them and we can automate it to battery cell assembling, we can also develop it more improved technologies for battery recycling. That is one of the key issues. So when you are making battery cells, you have to also think about the sustainability and try to find some new solution for more ease recyclability of the cells. For example, to improve the mechanical treatment in the beginning of cell recycling. And last but not least, of course, there has been a lot of discussion about the use of the critical raw materials in batteries. And that is one issue we like to look at as one option of the work. So how to go towards the sustainability batteries? One, what we have already started to work with, which is a worldwide research question, is the replacement of the existing liquid electrolyte with the solid or semi-solid electrolyte. In this project, we aim to use materials, solid or semi-solid, but they should be in the powder form, and thus they are possible to be printed. Then we already have one solution to replace this toxic solvent. We have tested it in our research facilities, and we know that we can make already the existing batteries more green, not only by print screening, but also for those using nowadays liquid electrolytes. Then this screen printing is one option also that we might have a possibility for new cell design. And thus, of course, we have a possibility by that way to increase the energy density in the cell. And that approach for new coating is also used and taken into account in every part of the cell component, not only for cathode, anode, but also for electrolyte. And then, of course, one role of our work is in a bigger scale also to look at some more advanced chemistry for the next generation lithium-ion batteries. So our specification for this project is that we use a solid-state concept for battery cell assembling, and we apply a screen printing. So it enables us to control the interfaces of the batteries better way. Cell design can be that stack design, which is very commonly used, but we also can focus on the coplanar type design. One of the key challenges is that solid-state electrolyte, so that we have an electrolyte which has a high ionic conductivity, not only as an electrolyte, but when it's operating inside the cell. So typically, the operation of the electrolyte inside the cell is not the same what we measure, for example, as the conductivity for the electrolyte material itself. And at the end of the project, we hope that we have at least a full cell prototype, which we can cycle very easily, so it has a good cyclability, and it is possible to manufacture from roll-to-roll processing. Cathode development is my core competence area. We have not put so much effort in this project for cathode development because we already have a very good solution for cathodes, for high nickel cathodes, for cobalt-free cathode chemistries, which we can also apply and utilize in this project. We have also developed earlier a lot of core competence for the lithiation of especially these high nickel materials, which are different materials for lithiation viewpoints than for example, earlier battery chemicals with a higher cobalt concentration. In this project, we have a short and small contribution to develop new type of the high voltage cathode materials like LNMO and also lithium-rich layered oxide materials, which are those advanced materials for lithium-ion batteries. Overall, our aim is that the concept we are developing should be chemistry neutral, so basically we can apply this concept independently on what is the cathode chemistry we use in the battery. A lot of effort is put now on the solid-state electrolyte concept, not only in our project but worldwide, and that's the reason we are working globally with some of the key universities and collaborators to find the solution for that. Currently, it seems that our solution will be some type of the composite solid-state electrolyte, what we will start to print in our cells. And at the same time, during the cell assembling and screen printing, we replace the harmful binders and the solvents from the system and then replace the liquid electrolyte with that semi-solid or solid powder we are coated on a cathode surface. So to conclude, on a general level, so far we have already coated by screen printing cathode and anode materials and without any challenges. So basically our cells work like our reference cells in the battery testing. There are several potential cathode chemistries already developed, and these high voltage cathode materials, which are now in the main focus, they really require a new type of the electrolytes for the battery cells. This screen printing seems to be suitable and chemistry neutral method for cathode and cathode electrolyte layers coating, and we can very easily, hopefully in the future, also control the interfaces. If you look at the research worldwide, there are a lot of possibilities for excellent solution for solid-state electrolytes, but more or less the key challenge is in the real battery application, the low ionic conductivity of those electrolytes or the air sensitivity of the electrolytes, which makes that they are not very easy to handle. And at the end, we hope that this sustainability of the cells can also be improved with that non-toxic compounds and fluorine-free components, which can also be applied already in the development of existing lithium batteries. Thank you.
Thank you, Ulla. My name is Riikka Suhonen, and I represent VTT, and I'm here today to talk to you about the printing technologies in battery manufacturing. Some words about our background at VTT. Already back in the end of 1990s, an idea came about this printed intelligence, which would be a new technological innovation derived from traditional paper and electronics industries. Printed intelligence covers printed electronics, which is the manufacturing of electronics using roll-to-roll production techniques, and also printed functionality, which you can imagine to be, for example, bringing some new functionalities into the traditionally printed, for example, packaging or printed media applications. So the printed intelligence in overall, it extends the functions of printed matter, for example, to the realm of photonics and functional electronic systems. The printed intelligence research today is employing about 120 people in Oulu and in Espoo. We have 5 teams working around this subject. Printed material systems, flexible electronics integration, printed electronics processing and biosensors are located here in Oulu. And in Espoo, we have part of the biosensors team and also a flexible sensors and devices team. In Oulu, we are also the home of the Printocent community, which is aiming to commercialize all products arising from the printed intelligence. In Oulu, within over these 20 years, we have built a vast pilot infrastructure. In these pictures, you can see photos of our roll-to-roll equipment, including printing lines, converting lines, evaporation, electronics testing line. We have an assembly and bonding line, hybrid assembly line, where we can assemble discrete components onto a flexible web, and also an injection molding line, all of which function in the roll-to-roll form. At VTT, our competencies cover actually the whole production chain. We start from materials, tailor them in the way that we can process them into components. In these pictures, you can, for example, see a completely printed OLED, organic light emitting diode, an OPV, organic photovoltaics, and also some sensors. And from these components, they are integrated in the systems. And in these pictures, you can see an example, a sensor patch and an overmolded LED display. Why would we choose printing? It brings us freedom in the design. We can introduce some new functionalities and concept architectures. It makes the integration easier and more, but most importantly, we see in these battery applications the cost effectiveness of the production. With these high volume roll-to-roll manufacturing technologies, we can speed up the processing of the layers and also save in the material usage. On the right-hand side, you can see a nice example of building integrated photovoltaics. And you can see that these printed photovoltaics, besides its energy harvesting property, it serves also as a decorative element as the building facade. Within this past project, the roles of project partners are listed in this slide. University of Oulu, so Ulla Lassi's group, is in charge of the cathode chemicals and the characterization of those, and also the recycling. Whereas at VDT, we are in charge of the printing in collaboration with the University of Oulu. So at first, we have the materials, we make them into inks, and then print them in the layers, and those layers are characterized, and in the end, we will be upscaling the production and doing the quality assurance of those roll-to-roll processed films and batteries. The big vision of this project is shown in this graph, where we have a roll of metal foil substrate, on top of which the cathode, the electrolyte and anode would be printed, and this all will be sealed then to a roll of batteries. Of course, everyone knows that this is a very simplified image. Between all these steps, there are sub-processes, but this gives you an image of our overall vision in this project. And then when we look at the battery stack structure or the cell structure, and looking at the layer thicknesses that are required, for example, for the cathode layers and the anode layers, when we compare the printing techniques that we typically use, screen printing, and in our case, rotary screen printing is an obvious choice, because we are aiming for tens of micrometers thickness, and this can be achieved with the screen printing. Then some results on NMC cathode inks. In these graphs, you can see rheology measurement data. We had 4 different cathode inks. All of them consisted of the NMC powder, a binder, some conductive additives, and a solvent. And cathode ink number 1 had the lowest solid content, and the solid content increases, and with the cathode ink number 4, has the highest solid content. And from these graphs, you can see from the viscosity graph that all inks are shear thinning, which means that the viscosity decreases with higher shear rates. And this is a desired feature in printing. So far everything looks very nice. What you can also see is that with this higher solid content, you can get higher viscosity inks. And what we see, for example, for the cathode ink number 4, is that the structure of the ink was broken with higher shear rates during this measurement. And already this leads us to suspect that this might result to an uncontrollable ink transfer in the roll-to-roll process, even at low printing speeds. In the rheology measurements, we also did an amplitude sweep. And from these measurements, we find out that all of the cathode inks have no flow point, which means that they stay in their viscoelastic liquid state throughout the time. And this is an indication that we expect these the printed layers to level quite nicely on the substrate during processing. Of course, depending on the viscosity level, if the viscosity is too low, then the inks might flow out from the screen at low printing speed or during the machine stops. Or they can also cause some spreading of the printed pattern. And in this next slide, we can see a video of the cathode ink number 4, which was the highest solid content ink. So from this video, as we already suspected from these rheology measurements, you can see that the printing quality or the quality of the printed pattern is far from perfect. The ink structure breaks down already at the low shear rate, low printing speed, and resulting into an uncontrollable ink transfer and a very porous printed layer. We also printed the lowest solid content ink, which was the cathode ink number 1, and you can see the video here. And with this lower solid content, as you saw quite nicely, the ink leveling is highly improved. There is still some slight spreading of the printed patterns that you can see on this picture at the right, which means that we need a bit of further optimization of the ink to get a perfect pattern printed. But all in all, it looks already very good. So to summarize my talk, I've shown you that VDT has a strong background in printed electronics, developing materials to components and building components to systems. We have chosen the rotary screen printing as the printing technology for the layers in this past project in the solid-state battery cells. We've shown roll-to-roll rotary screen printing of NMC cathode inks, and these, like Ulla already mentioned, have been tested in battery cells, and their performance is very much comparable to the traditionally coated layers. Our current focus is on the development of a printable solid electrolyte ink, and from this we will show then new results in our next webinar. So thank you for your attention, and I give the floor to Jukka.
Yes, thank you. I'm Jukka Säkkinen, Head of R&D in Oulu University of Applied Sciences, and I'm going to tell you about application development and testing, especially Nuvi Lab research environment that we are currently constructing in Oulu. There are two key drivers that currently affects on vehicle development. First of all, the climate change and tightening environmental legislations is leading towards zero emissions. And this leads that the traditional internal combustion engine will be replaced by multi-fuel, hybrid and electric power sources. And this is already happening, as we see in personal vehicles, but also in commercial heavy-duty vehicles like lorries, buses, construction machines, mining machines, and so on. So there is a need for good battery solutions and different kind of applications for the future machines. The other key driver is the development of automation technology, sensors, and artificial intelligence. This development enables more advanced driver assistance systems to be developed and implemented, as well as fully autonomous vehicles to be developed. What we are doing, we are actually building up a research and development environment, Nuvi Lab. It will be an independent research environment to develop new energy efficient and environmentally sustainable autonomous vehicles. Environment will be established in Oulu, in Linnanmaa campus, which is one of the biggest university research communities in Northern Europe, with around 4,000 employees and more than 25,000 students. And next to campus there is Technopolis that is providing offices and services for companies that are willing to locate in Oulu, even for temporary purpose. The environment is funded by European Union, European Regional Development Fund and Interreg Nord European Regional Development Fund, and many companies has also participated in the funding and City of Oulu. In the campus area we also have 5G test network that is covering also this Nuvi Lab environment, which gives us possibility to develop this kind of remote control of vehicles. And 5G has the capacity to actually do it in real time. So this is one plus that we can provide in our coming environment. So this Nuvi Lab environment is to develop environmentally sustainable and energy efficient utility vehicles and passenger cars, using multi-fuel, hybrid or electric technologies and various energy storage systems. But also to develop autonomous vehicles. We have hardware in loop simulation capability in our environment. And if you would like to see more information about this Nuvi Lab, please take a look on the link that is given in the material. The heart of the environment is four-wheel drive active dynamometer with a maximum power of 1.8 megawatts and maximum torque per wheel is 25,000 Newton meters. We can test vehicles up to weighing 50 tons and not only entire vehicles but also powertrain systems and standalone electric motor measurements can be done in our environment. The supplier of the system is Horiba Europe GmbH, which is recognized to be worldwide as one of the leading suppliers of these kind of systems. And we have a clear vision how to develop our environment in the coming years. To open up this term hardware in loop, or should I say dyno in loop, we are going to show you a short video which describes the basic principles of the system.
The new era of machines is here. Nowadays, utility vehicles are still mostly driven by humans. These quite simple and boring tasks bind human resources and cause health issues when workers spend long periods of time in a sitting position. So there's a strong desire to break the binding between man and machine and let people do something more productive. In the future, fully autonomous utility vehicles will do these simple tasks in a desired manner, safely and independently without human interaction. Intelligent features of autonomous vehicles lower emissions and make them more environmentally friendly. With optimal route planning, they also enhance overall productivity. However, the development of such machines is very demanding, and when it comes to testing, one approach is to build a prototype and let it loose to see how it survives. This raises many safety issues and can cost quite a lot of money. But now for the good news. We are building a unique test facility for the utility vehicles in the campus area of Oulu University and Oulu University of Applied Sciences. This new facility is called Nuvi Lab. In Nuvi Lab, you can connect your vehicle's powertrain to a modern active dynamometer and test it in a fully equipped laboratory environment. And in case you're developing an autonomous vehicle, you can connect the AI of your machine to our Nuvi system. In Nuvi system, you can do the development of your machine in a fully virtual environment. It offers realistic physics modeling with realistically behaving environment. And it's a good place to develop the AI of your machine while it's operating in virtual reality. And of course, you can safely let it loose and see how it behaves in different situations. This development facility is made in collaboration with some of the top research groups in Northern Scandinavia. In Nuvi Lab environment, you can develop your next world-class utility vehicle with the help of our professionals. So, if you see that the Nuvi Lab facility would benefit your R&D, don't hesitate to contact us.
Yeah, one of the key issues in the environment is that the dyno is active, which means that we can adjust the running resistance for each wheel separately. So if in this picture we have a digital model of the vehicle to be developed on the left, when the vehicle moves uphill on the modeled working environment picture on the left, the running resistance will increase in dyno where the actual developed machine is attached. So this gives us possibility, for example, to simulate regeneration when the machine is going downhill. And in this picture, we have on the right side we have a picture of Narvik harbor area, which have been modeled on the left picture into our Nuvi Lab system. And the idea is that we always make a model of the final working environment of the machine to be that it's developed. The environment might be farm, field, forest, town, mine, or even battlefield. What is the final application environment for the vehicle that is being developed? The benefits of the environment is that the tests are repeatable, and it will create significant reduction in development lead time and also in prototype costs for the companies. The hill simulation environment and its opportunities are already available for the developers. We have received the automation system from Horriba in the beginning of this year, and we have already built up end-to-end loop for the system. But the actual dyno will be assembled and then taken in use at the end of this year. So the whole system is up and running in the beginning of next year. And to be honest, I'm excited about the opportunities that this environment is going to provide companies, researchers and research institute to research and develop the future vehicles that we are going to need to tackle the environment challenges that we are facing. So I'm looking for cooperation with all of you that are working with these questions and developing the solutions for the future. And we will be moving on. I will give the stage to Ulla. Ulla, please.
Okay, before we will end in the seminar today, I have found some questions from the audience, and there were 3 questions related to that project. Thank you for those questions. The first question was related to ionic conductivity of those solid electrolytes, and as I already mentioned in the first presentation, so ionic conductivity of the solid electrolyte, it is a key issue. Of course, when we go from liquid phase towards a solid phase, the diffusion of the ions will be slower. And there might be also some mass and heat transfer limitation inside the battery cell. What we have measured, we measured for the solid state battery electrolyte, we measured the ionic conductivity already before we will use it in the battery cell. And typically those conductivities we measure are higher than that what we then see in the real battery cells. And of course, this is some key issue for the project also, and we can do something, we can improve the conductivity also in solid state reactions. The second question was related to anode material. That is sure, I didn't mention not at all about the anode. The reason for this is that basically we already have an existing solution for anode. We can use carbon-based anode, and of course we have for the future with different chemistries also, for example, lithium titanate anode materials, which is very potential material in the future. These anode materials we have already tested for screen printing, and we have compared them for Dr. plate coating, and I can say that we already have a solution, and basically the behavior is equal to that what we have already in the existing commercial battery cells. And of course, in the future, metallic lithium foil would be one good option if we coated it. And that is also one reason what we are doing in collaboration with one of the international research unit. Then there was also a question related to the role of the companies. Yes, that's a good question. Companies are, of course, very important because we are working so close to a real application, and we have a lot of companies we have actively discussed on this project. Of course, all the other companies are also warmly welcome to join because that is an open and public research. For example, here in Oulu area, we have a lot of companies already working with the print screening technology, but not with that application. So at least I, as a PI of this project, I see that there is a lot of now good potential to combine this competence from print screening to the competence we have of making battery chemicals, and I hope that we will see application related to this project very soon.
Thanks, Ulla and Jukka and Riikka. That concludes our scheduled programming. If you still have questions, feel free to write them to us by clicking the link below, and we will answer those questions and upload those questions and answers to our project website, to which there is a link down below as well. And these slides can already be found from the project website, and any upcoming updates and results will be also uploaded to the project website. Here is our contact information. If you are interested in, for example, cooperation, hit us a message and let's discuss. And that's all for today. Thank you for your attention and stay safe.